Chapter 9, Chemical Equation Calculations. We learned how to write and balance chemical equations, and now we're going to learn how to get even more information out of these equations. We can interpret equation coefficients in different ways. So we can look at this balanced chemical equation here, which shows how nitrogen monoxide gas from exhaust reacts with oxygen to form nitrogen dioxide gas, which is a major component of smog. And UV light is a catalyst for that. And we could say that two molecules of NO, pictured here, one molecule, two molecules, react with one molecule of oxygen to form two molecules of NO2. And I think we're all okay with that by now. But what if we multiplied everything by 12? Would the equation still be true? If we had 2 times 12, 24, that's 12 is a dozen, isn't it? So I probably have the wrong color here. No, I actually have black. That'll work. What if we said 2 dozen of NO reacted with 1 dozen of O2 to form 2 dozen. I didn't write small enough, did I? Would that be okay? Right? We just multiplied everything by a dozen. What's the chemist's dozen? Avogadro's number, a mole, right? So we could also say 2 moles of NO. That's one of my favorite compounds. It looks like no, right? Because all caps is shouting. 2 moles of no plus 1 mole of O2 will produce 2 moles of NO2. First time I wrote too big, second time I wrote too small. You can't win. This gives us relative amounts in terms of numbers of particles. Okay? The mole is a counting unit. It's a particular number of things, just like the dozen is a counting unit. We can also interpret these equations in terms of volume. This only works with gases, though. So Avogadro's theory is that there are equal numbers of molecules in equal volumes of gases at the same temperature and pressure. This is not true for liquids and solids. It's true for gases because there is so much empty space between the particles that the size of the particles doesn't matter at all. So we can interpret this as 2 moles plus 1 mole gives us 2 moles. We can also interpret this in volumes. And you can use any volume unit that you find convenient. Liters or milliliters is probably what we would commonly use. But, you could do cubic yards if you felt like it. But that's not a very scientific unit. 2 moles of nitrogen monoxide is going to have the same number of particles and occupy the same volume as 2 moles of NO2. 1 mole has half as many particles as 2 moles, and so it will occupy half the volume. We can just swap out these moles in here for volume units. We can say 2 liters of nitrogen monoxide gas plus 1 liter of oxygen gas is going to form, that was a bad arrow, 2 liters of NO2 gas. That's provided that everything stays the same in terms of temperature and pressure. We could also write this 2 milliliters and 1 milliliter and 2 milliliters. So we look at this equation, and if we started with 2 liters of NO, we could make 2 liters of NO2. So these are useful, practical types of calculations. Any questions yet? So we can interpret chemical equations. All of them can be interpreted in terms of ratio of molecules and ratio of moles. We can use ratio of volumes for gases only. Here's a generic equation. 2A plus 3B forms C plus 2D. The coefficients give us the ratios in terms of molecules, in terms of moles, in terms of volumes, if they're gases. They all have to be gases. So what is really the most useful is this mole ratio. If we start with this many moles of reactant, we can predict how many moles of product that we will form. So, given the chemical equation for the combustion of propane, balance the equation and interpret the coefficients in terms of moles and milliliters. So we'll get a little practice balancing equations in here. Sometimes equations are already balanced without any coefficients. Is this one balanced? No. No such luck. These combustion ones, I just like to start on the left with carbon. I have 3 carbons on this side, and I only have 1 carbon on that side of the arrow. So let me use a color that's going to show up here. If I put a 3 in there, that'll balance the number of carbons on each side. Do you remember this? And then over here I have 8 hydrogens, and over here I only have 2. But if I multiply this by 4, 2 times 4 is 8. So now I've got 8 hydrogens and 8 hydrogens. And I like to leave oxygen for last because oxygen is in 2 places over here. So here I've got 2 times 3, which is 6 oxygens in that one, and 4 oxygens over here. 6 plus 4 is 10. And so over here I need a 5 in front of the oxygen. So brief review of balancing chemical equations. Now we're supposed to interpret this. So A says in terms of moles. There's no coefficient in front of this one. How many moles would it be? 1. Chemists have this thing against the number 1, right? So bless you. See, she's becoming a chemist. She's allergic to the number 1. 1 mole of C3H8 will react with how many moles of oxygen? 5. Sometimes this seems like voodoo or something. All I'm doing is I'm inserting a unit between the number and the chemical formula. So 3 moles of CO2 plus how many moles of water? 4. 4 moles of water. Now, could I stick grams in there? No. Why not? Well, they're gases, but do grams relate to counting of atoms? No. It has to be a counting unit because this says 1 molecule reacts with 5 molecules. That does not mean that 1 gram reacts with 5 grams. This is in terms of numbers of particles, so we can use moles. We could use dozen, but it's not useful. If they are all gases, we can also use volumes because for a gas, the volume is proportional to the number of moles. You double the number of moles, you double the volume. And that's a special, strange property of gases. So then interpreting this, because all of these are gases, right? We could also do this in terms of milliliters. 1 milliliter of propane reacts with 5 milliliters. And this is forming 3 milliliters of CO2 and 4 milliliters of water, all gases. Any questions? We've talked about the law of conservation of mass. That says that mass is not created or destroyed in a chemical reaction. And so we can verify this. The combined masses of the reactants have to equal the combined masses of the products. And there's a big blank there, and I don't remember what I was supposed to write there. I don't remember. So we'll make something up. Let's do this in atomic mass units and think of this in terms of molecules. In terms of atomic mass units, how would we figure out the mass of 2 molecules of NO? We need the periodic table, right? So 1 molecule of NO, it really helps to select the pen tool. 1 molecule it's got 1 nitrogen atom and 1 oxygen atom, and I think that comes out to 30.01 atomic mass units. So there's 2 of them, right? Each weighs 30.01 atomic mass units. And then how much does a molecule of oxygen weigh? 16 times 2, right? 32 AMUs. And now we're hoping that this is going to equal 2 times the mass of that one. Well, that one is 14.01 plus 2 times 16, which I think is 46.01. I forgot to get my calculator out, as usual. So see if you can catch me making a stupid mistake. I'm going to get my calculator out. So on the left, we've got 2 times 30.01 plus 32. So over here, the reactant side, if we did this reaction in terms of molecules, the reactants would weigh 92.02 AMUs. And on the right side, we end up with what? 92.02 AMUs. Is mass conserved? Yes. The mass that we started out with is the mass that we end up with. We didn't gain mass, we didn't lose mass. And when you think of this in terms of atoms, like Lego blocks, you're just taking this little creation of a nitrogen and an oxygen, you're taking it apart, and you're taking this one apart, and you're putting them back together. Let's go back to the picture. This picture. Here we had 4 red balls, and we end up with 4 red balls. They're going to weigh the same, right? 4 red balls weighs the same as 4 red balls. And we've got 2 blue balls and 2 blue balls over here. So it should weigh the same, right? And if we calculate it, it does. Now, where was I? Okay.